Hello, everybody. So here it's Jens speaking from Hamburg, from the Olympus organization, and I say welcome to all of you who is listening or are listening to this webinar. So we have two speakers, two very, very experienced speakers, one about NDT, this is Florin Turcu, also from the Olympus organization. He will talk about corrosion inspection, especially when it comes to the Epoch 6LT. And afterwards, Hanna from also Olympus will talk about how to save time, save money. You see this on the screen already with RVI inspection, so remote visual inspection technologies. So I'm very happy to have those speakers on the line. And first, I would like to shortly introduce the question options. So you are all muted, but of course, you can always paste your questions. Either you raise your hand, then we can afterwards unmute you and you can speak out live, or you simply post the question in the question pane of this control panel of the webinar. And we can read it, of course, and after the presentation session, which will take roundly 30 minutes, we will answer the questions if there are some. Okay, for a moment, thank you that you're on the line and thank you for the presenters. And I would say I hand over to Florin for the first presentation part. Florin, can you hear me?
Yes. So good afternoon or good morning, everyone, depending on where you are. Today I will talk about the new our new flow detector, the Epoch 6LT, and some specific features that we have added recently concerning the corrosion monitoring. So there's just a few subjects for 15 minutes. I will reintroduce, let's say, the Epoch 6LT flow detector, and will let you know what the advantages, what the benefits for using this flow detector would be for you. Then I will introduce the problems for measuring the remaining wall thickness when corrosion is present, how we can do corrosion monitoring with the Epoch 6LT, and about rapidity, accuracy, and reliability of measurement. I think just a year ago, Olympus had released a new and ultra portable, let's say, flow detector, which is the Epoch 6LT. It incorporates 90% of the ultrasonic capabilities of its bigger brother and the well-known Epoch 650. Among these, I can remind pulsar performance, digital filters, the very, very good signal-to-noise ratio, the same screen size, and also the classical sizing algorithm, the DAC curve or the TCG, DGS or AWS, and so on, and all this in less than 1 kilogram. So, like we said, a powerful flow detector in the palm of your hand. So you can use it with one hand only. You can operate it with one hand only, while the other hand can be used to screen or to measure with a transducer. What you can do with this flow detector is to perform weld inspection in tough environments with more comfort than previously, and you would not give up to the data quality. About the versatility of this instrument, if we take a classical case of inspecting a vessel onshore or offshore in a chemical or a chemical plant or in a refinery, we all know that this would be one of the most complex components to be most of the time fully inspected, because you can find all the applications from welds to bolts, cracking, inspecting for corrosion, inspecting the supports, the flanges, and so on. How much can we do out of this with the Epoch 6LT flow detector? Instead of using a full kit with, let's say, a flow detector, a thickness gauge, and plus the probes and all the rest of the material, only one instrument very light and portable, could be used. So the epoxy XLT could be used for most of the weld geometries for weld inspection in conventional ultrasonics. Even if you would have a cladded vessel, for example, with cladded internally with stainless steel, or if you would have some dissimilar weld. You have here in the picture on the right side a test, let's say, on a dissimilar weld from oil and gas industry with using TRL probes. So even this can be done with the powerful ultrasonics that we have inside the epoxy XLT. Above this, you can also detect the laminations on, let's say, on the main body of the vessel. You can also do corrosion thickness gauging. So with the latest release of a new software option, there is no need for additional thickness gauges. You would have a thickness gauge incorporated into the epoxy XLT. And you will have no compromise on the precision of measurement and the quality of data. We will see this a little bit later. Now, let's start with the problematics of measuring wall thickness when corrosion is present. So we all know that when corrosion is present, the back wall is very irregular, which means that if we would use a single crystal transducer, the sound would be scattered away from the transducer. So because of the rough back wall, most of the sound intensity will not arrive at the transducer itself. It means the sensitivity would be very low, especially in the case of pitting. The solution against this, and what has been used for a long while, is using twin crystal transducers. Twin crystal transducers usually incorporate two piezoelectric elements acoustically separated, one used as a transmitter, the other one as a receiver, and under a geometry forming a roof angle to generate a V-path shape, a V shape of the beam. This V shape or V-path would focus the sound at the base of the pit, and in this way you would have a lot more sensitivity from the corrosion. However, in this case you would need to correct the path, the sound path, because you would not have otherwise you would not have the right thickness, and you also need to a specific algorithm to improve the sensitivity, like high amplitude and zero crossing measurement. Now, what would be the technical issues to measure the remaining wall thickness? If we do thickness measurement on corrosive components, usually performed with a thickness gauge for better precision of measurement, this would be achieved by the use of dual transducer, as I said previously, and using a specific algorithm to include auto gain control, V-path correction, and zero crossing detection. In any case, a flow detector could be also used for corrosion inspection and would be also preferred due to the possibility to control manually the gain, to display the waveform on a big screen, and the possibility to set the gains, the gates, and also alarms. All right, so what would be the compromise between these two? Can we use both of them in the same time? Well, epoxy XLT provides a dual mode, let's call it dual mode capability, while the corrosion software is activated. So let's take the corrosion software. It would provide a flow detection capability and a corrosion gauging option. What does it mean? So in flow detection, you see some images here. You can switch between these two modes only by pressing a button, like you see here, corrosion mode, and FD mode. But what does flow detection mean for us? It means that you have control over the gauge, you have control over your gain, and you can set the alarm, at least. It means that you can screen very fast, you can detect quite well, and you can get an alarm as soon as you have a very low thickness. What about corrosion gauging? It means that the gain control is automatic, so you cannot control it manually. It is controlled by the instrument, and it is increased increased a lot, saturated, so that you can detect in the zero crossing. And you would also have the V-path correction. All this translates into a very high accuracy, about 0.01 of a millimeter, very similar to that of a thickness gauge. So how do we do it? Of course, we need to calibrate. So let's start first. We calibrate while in flow detection mode. We're using a step block. You have just 3 steps. Put your transducer on the thin block, collect the data, put it on the thick block, collect the data, and then you are calibrated for FD mode, so flow detection mode, and using the gate. You have the gate positioned at the area of interest. You can set an alarm, and you will know when you detect something. Then we need to calibrate for corrosion. We move to corrosion mode by pressing the corrosion button. Then we go to calibrate, and we calibrate for using the step block again. And the precision of measurement is outstanding. What we do next with the calibration, actually, very important, we have now 2 different calibration in the same setup. So it's a kind of multi-mode or multi-group setup. So we are ready for the inspection. If we have, let's suppose that we have to inspect a suspected area for corrosion, we would switch to the FD mode, flow detection, and set the alarm for low thickness. So you see here, the transducer has been recognized automatically. You are in FD, flow detection mode, and we have an alarm activated. So while screening, we screen the plate, we will notice that at some point the amplitude is lost, probably due to some pitting geometry, and we have a measurement. Of course, the measurement will not be perfect because of the loss of amplitude, so we lose some precision. However, we have an alarm because we detected something. We switch to the corrosion or thickness gauge mode by pressing the corrosion button, and immediately the instrument would increase the gain automatically, and it will detect at zero crossing. And the precision of measurement would be of 0.01 of a millimeter. So we have a very, very good precision only by pressing the button. What we do next, we just save the data in our grid, in our color grid, and then we can also export it to the scientific cloud. So what will be the results? We rapidly screened a suspicious area. We reliably found the critical points of pitting. We measured the remaining wall thickness with a very, very good accuracy. And then we generated a report, which in seconds is made available for review in any remote office. So we are very efficient. And all this can be done with an Epoch 6LT, with a very light instrument, but very powerful. Thank you very much for your attention. And if you have any questions, you are welcome to ask.
Thank you, Florin. Thank you very much for your presentation. That was really interesting. I would say we shift the questions to the end of the webinar. And then I would welcome the next speaker, who is Liam Hanna from the UK. So he will talk about RVI instrumentation and also how to save money, how to save time with RVI instruments. So Liam, you can start showing us your screen. Perfect. Thank you.
Hi everyone, and good afternoon / good morning, as Florin said, depending on where you are in the world. So my presentation today is focused specifically on remote visual inspection, and we look at probability of detection and how increasing that will help you as a user save ultimately time and money, which is the ultimate value when it comes to the inspection techniques in which you're employing. I'll start off with some basic introduction in terms of what is remote visual inspection. I'm very aware that a lot of people that are listening will be from an NDT or say UT/PA background as an example, or eddy current, so RVI might be quite new. I talk about the advantages of remote visual inspection in general, and then look at a very specific application within power gen or oil and gas, which is rotating machinery and specifically turbines, and then finally how we can overcome the challenges we faced and therefore save time and money throughout the inspection of these types of components. So in terms of remote visual inspection, it's very, very simple. by visually inspecting something, it's easy to understand the whole situation, and therefore a very complex idea can be portrayed in a simple image. Remote visual inspection extends the reach of the human eye into areas that would otherwise not be able to be inspected. To put that into perspective and compare this to other techniques, if we look at the people that are available in this online room now, probably 50% of us will be able to understand this. So sort of using phased array, looking at some various different scans here, using I think an OmniScan, looking at this eddy current pattern again. Only a few of us will be able to understand this. And then if we look at a metallurgy report, again, probably even less of us will be able to make some sort of understanding of what this is without having a reference to work against. Conversely, if we look at remote visual inspection and we look at this image here, it's very easy to understand this and draw a conclusion from this and decide that, yes, there is quite clearly a problem here. So although we can say photographs can be subjective, they do demonstrate immediately and very, very clearly if there is a problem. And this is the fundamental principle of remote visual inspection. In terms of advantages of remote visual inspection, I've broken this down into a combination of probably cost and time. From a cost reduction perspective, human resources and the amount of time that it takes to physically disassemble a component or a part, specifically a turbine or any rotating machinery, takes a long period of time to physically take this apart and inspect this visually. If you can remove some minor components and introduce a video scope, then in a much shorter period of time, you're able to carry out this type of inspection. In terms of time management, in terms of any time, anywhere, anybody, there's no specific external qualifications required. Anyone can carry out remote visual inspection. You may have some internal requirements that you have there. It enables for an internal visual inspection without the requirement to take everything apart. It's very, very simple and easy to operate. We make lots of jokes, even within Olympus, about it fundamentally being a camera on a stick, which is very much what this is. But like I said before, it's something that enables you to extend the reach of your human eye, your general eyesight, to be able to understand what something looks like inside without having to physically take that apart. It's easy to transport and move around. From an autonomy perspective, all of our equipment has the option to be powered by battery as well, and it enables you to work in relatively small areas. We understand that around the plant or working on some various types of rotating machinery in different locations, you've got sometimes relatively confined environments in which to work in. So therefore, being able to move around with the equipment, place this in a comfortable position and work on it for a period of time, sometimes hours, becomes even more important. It's important to notice at this point that remote visual inspection, as mentioned already, is a visual inspection, and we have the ability to measure some of the defects that we do find. However, for subsurface and internal defects, we do have other products which this can be used in conjunction with. A good example would be non-destructive testing, such as using eddy current or ultrasound, as Florin was mentioning just before me, or even with analytical instrumentation. It may be that you've got a reading of some wear materials in some product that explains that this could potentially be this part failing here. Then you can then go in afterwards and check that specific part with remote visual inspection to see if that is the case. If we take a relatively specific topic now, because we've got very limited time to talk about this, and obviously there's hundreds, thousands of tens of thousands of different applications that we can discuss when it comes to power generation or gas chemical. So the part I'll focus on here specifically is looking at power turbines. So sometimes aerospace derived turbines used for power, but generally power turbines, and specifically the hot section of these, so from the combustion chamber backwards into the turbine section. As we are probably all aware, the temperatures within these can reach very, very high temperatures, well in excess of 1,000 degrees, and well in excess of the melting point of the materials that are used inside these type of environments. To try and combat this, is a combination of different cooling holes, which are introduced to try and allow a comparatively cooler buffer from a bypass to maintain some sort of comparatively cooler air pocket across the front of these blades. Also, they introduce things like thermal barrier coating, which tries to, again, reduce the effects of the temperature. So one of the most common inspections, specifically in the hot section, is looking at these turbine blades, nozzle guide vanes, the combustion chamber, etc., to see if there's any loss of coating, to see if any of these holes have been blocked, for example, which could cause wastage in the future. The difficulty is in some of these environments is a real combination between high contrast and low contrast environments. Therefore, the stresses that are put on the type of camera that you use is quite high. It's not like taking a photograph in a normal environment. The environment is generally dark with a lot of low contrast features, and then you'll have something that might be very, very reflective, or the opposite, which completely throws out the way in which a camera works. The working environment in which we're working is often small, which forces an inspector to try and secure a place to install the endoscope, and you're not always working in a perfect environment. And you generally have to move around carrying the scope with you to different locations. Like I mentioned, the most common defects that we're going to be looking for are things like blocked cooling holes, loss of thermal barrier coating, and things like burnout, so blades or nozzle guide vanes where these holes generally have either been blocked or opened up completely and have started to burn through. So these are some of the basic understanding of the application itself. When it comes to overcoming these challenges, and most importantly doing that in a cost-effective and efficient manner, while still maintaining quality, this is where I'll talk a little bit more about some of the products that we've introduced to cover this. So if we look at some of the typical defects that I mentioned on the previous page and along the top line, this is mainly things like, you can see here, this hairline crack, some melted material. Got an example of a fuel nozzle here. Again, a good example of somewhere where there's a real difference in contrast across the image itself. So we've got a relatively reflective center and then a very, very dark outside. Combustion chambers, again, generally very, very large places. They use a lot of light. They therefore require a lot of light, and we'll talk about that as we go. And then various different types of blades as we have here. One of the key differentiators when it comes to our latest product, which is iFlex NX, is the ability to actually pump out more light. So the actual we use a laser diode, which is much more powerful than a standard LED or a light emitting diode. And this is actually 4 times brighter than a conventional video scope, than the standard video scope that you might be using either at the moment or elsewhere. There's 2 key benefits to this. One is that, yes, you've got a lot of light to be able to use and pump into certain areas, but in conjunction with a new processor that we have, it's called Pulsar Pick, this intelligently will react to the environment in which you're looking in. So we always talk about more of this, more light, more power all the time. However, there's some circumstances where you actually don't want more. So what is more important is the quality of this light. So with the Pulsar Pick processing system that we have here, in conjunction with this laser diode, we have the ability to increase or decrease the illumination intelligently and automatically inside the scope without having to touch anything, to balance out based on the type of environment you're looking at. The 2 most difficult things to take images of are generally very, very reflective items or very, very light-sapping large areas which use a lot of light. Unfortunately, within all of the environments in which you guys work, the only things you take images of are very, very reflective or very, very dark items. Therefore, this intelligent adaptation really does help to maintain good, balanced images, because when it comes to photography, light is the most important thing. Moving forward from that, what we've actually managed to do is we've got a new high definition sensor which is used in the tip of the scope. And when you increase the pixels, as an example, when it comes to high definition, you have more pixels. More pixels gives you potentially more resolution. The problem you have there is that by introducing more pixels across the same surface area, these pixels then become slightly smaller, and therefore their light capturing ability is not as good, even though the resolution will become higher. This is why we introduced the laser diode system, which means that we can actually maintain 4 times brighter than a historical video scope, and also obtain very, very high levels of resolution. This is quite difficult to see in a standard environment looking at a PC screen. One of the things that I wanted to point out is that by increasing this resolution, the zoom function, which realistically was not a major function historically, becomes much more useful now. So if we look at the image on the left-hand side, this is just a slight zoom. I think it's probably 3.5, 4 times zoom of the part on the right hand side. And what this enables us to do is get a little bit more detail in areas where we may not be able to change a lens or we can't physically get closer. It becomes much more useful now. Something that is definitely not possible with conventional video scopes. The next thing we've tried to introduce as well, or we've increased, is a wider color palette. We've got 4 times more colors available to iFlex NX than we had on our previous video scope. And this does 2 things. One, obviously, color reproduction is very, very important for all types of inspections, specifically within this type of environment. If you can imagine, if you're inside a turbine and you're looking at some thermal barrier coating loss as an example, you need to have a good understanding of color, because then you can see the transition between the TBC and the metal underneath. Equally, if you're looking at weld samples or welds within pipes or heat exchangers as an example within a plant, the heat affected zone is very, very important, and therefore the color and the understanding of that color is also very important. By having more colors, we have more potential to be in line with the true representation of the colors that are available. On top of this, having more colors available means the scope and the processor spends less time hunting for colors that don't exist, which is where it can historically introduce something called color noise, which is where you see some grain coming across where the scope is hunting for a specific color, it can't find it, and it generally will introduce like a gray or a white pixel, which makes the image not look very good. So if you look at the example here, on the right hand side we have iFlex NX with the new color space and the new processing power. On the left hand side we have this a conventional video scope without that power. All of this together increases the probability of detection. So probability of detection being the amount of chances that you have of finding a problem. If your probability of detection is high, you've got more chance of actually finding a defect or finding a problem before it becomes a much bigger problem, which ultimately should save a lot of time and a lot of money. Moving on further from this, we've talked a lot about the type of improvements we've made to the inspection procedure and how to increase illumination, increase resolution, etc., etc. One of the important things is sometimes when you do find the defect, specifically if it's inside some rotating machinery, specifically if we're looking at a blade within a turbine, as we can see on the screen here, it's important to actually quantify that and actually carry out a measurement and find out how big that defect is. Is it within tolerances? Is it in line with what is acceptable within the maintenance manual? Do we just want to track this to see how it is changing over a period of time? If you look at the screen at the moment, you can see in the top left-hand corner of this blade, we have the view that you would generally see from a conventional video scope. With iFlex NX, due to the increased illumination, better optics now and a new processor, along with this new CCD, we have the ability to measure 4 times larger measurable area than you would with a conventional video scope, which means that measurements of larger defects can be taken from further away. If we look at this blade here, we can see there's a couple of marks here, this mark here specifically. If we have to do a measurement that tells us how far away this blade is, this mark is, from the root of the blade, occasionally you'd have to take 2, maybe 3 different measurements. Now, using iFlex NX, you've got the ability to carry all of this out in one. And again, this video demonstrates this quite nicely. So basically stepping from the fact that on a conventional video scope, you'd see around a quarter of what is actually available to be viewed and measured with the new iFlex NX. This finally brings me to the conclusion. Again, sorry we had a very limited period of time. But in summary, for obvious reasons, fast inspections are highly beneficial to plant output. If you can carry out your inspections faster and easier, it costs less money in terms of the inspection requirement. Equally, it means that you can have the plant up and running for longer, therefore downtime is lower. If you're an inspection service provider, this means you can actually carry out more inspections and actually be earning more money frequently. The ability to measure wide angles, the software and navigation and the understanding of the system itself is very, very simple. The bright illumination system, the intelligent adaptation of this, and simple articulation, and the increased probability of detection all helps within iFlex NX to try and minimize this downtime, and therefore maximize the profitability of the plant or of the inspection company from an efficiency perspective, being able to carry out more inspections, and therefore the inspector is earning more money by inspecting more of the time. The end of my presentation.
Thank you, Liam. Thank you very much from my side. Thank you also, Florin, again. It was really impressive and interesting. Now it's your time to the whole audience. So you have maybe questions to the both speakers. I don't know, Liam, Florin, did you receive any question?
I've got one. I've got one. This is a separate question here. It just says, how long does it take to carry out a measurement? I'm not 100% sure exactly what that means, but basically, with the way in which the system works on IPEX NX, with a measurement adapter attached, you've got the ability to carry out a measurement as standard. You've got the slightly wider field of view now, which means that you can use that single screen option if you need. When you get to a defect, you've got the ability to understand some of the environment before carrying out that measurement. So it's something we've introduced called spot ranging, which gives you a 3D plot on top of a surface. So if you're looking at, for example, a small dip or a dent, you can place this 5-point circular target on top. It gives you some indication of how far away all of these different points are from the scope itself, which gives you an understanding of what the surface looks like. And this is all before you've carried out your measurement. It also gives you a nice traffic light style understanding of how close you are to the item to be measured. So, for example, if you're in the green zone, it's going to be more accurate than if you're in the red zone. And then once you carry out this specific measurement itself, you just press the measure button, and this enables you to carry out various different measurements. So from seeing a defect to physically measuring that defect and having the data with you is all completed well under a minute, probably around 30 seconds. So it's very, very fast and very, very simple. It does not take a lot of training either. Within probably around an hour of training, you get a good understanding of how this works. And after that, it's just practice and how to interpret your results.
Very good. Thank you. Thank you for the answer, Liam. Are there any other questions from the audience? So Ahmed is asking, he's asking for a remote visual inspection. Is it similar to a condition monitoring method? You read it already, Liam, right?
Yes.
So he's asking, is it similar to a condition monitoring method whereby sensors are permanently placed on the equipment in question to monitor the true state of degradation via a monitor in the control room in real time?
So the answer is it completely depends on the user. Most of the time, this will be done as like an in-service inspection or during a shutdown. There's your main two options. It's normally used in conjunction with a condition monitoring system. So, for example, say you have some vibration sensors that tell you that this part of the machinery is vibrating at a level which is not expected, which would indicate maybe an unbalanced shaft or increased wear on a bearing, as an example. This may be, it's always going to be cheaper to remove some small parts to be able to introduce a video scope to go and look at that to see if there is any wear. Then you can measure this to find out if there is any differences, and then all of this data can be there's a condition monitoring system included free of charge with the Olympus video scopes called InHelp, and this is a combination of condition monitoring, trending, and report generation, where you can just basically map the same type of inspection over a period of time and review to see how this changes. But generally, there would be a condition monitoring system in place, and then remote visual inspection would be used at a point of entry to go and check to see if there really is a problem, if you're getting a false reading as an example, or to determine what that problem is before stripping down the machinery. A good example being wind turbines. So wind turbines have lots of different sensors placed them in all different types of places. And when you get different types of vibration, this generally indicates whereabouts within a gearbox the problem could be. So you can then go and inspect that environment, and you can see, is there some debris inside here which can be removed? And again, you can remove that using different remote visual inspection tools. Or could it be that you've seen some physical wear, some pitting, some toothing as an example, and at which point you can then make a decision, do we need to strip this down, or can we continue running this for a period of time?
Okay. If there are no more questions from the audience, I think you had a good chance. Of course, you can also give us a feedback after the webinar stops and contact or place your question then. For the time being, I would say thank you for everybody listening, and a big thank, of course, for both speakers. So brilliant job. Thank you a lot. And from my side, I wish you a good rest of the day, of course. So thank you again, and see you soon. Bye bye.